contact. Okay, the Schottky barrier is formed when a metal such as aluminum is brought in contact with a moderately doped n-type semiconductor. Generally, metal semiconductor is formed when you are going to in a conventional PN junction. If you remove the P region and when you introduce a metallic region, that is how metal semiconductor junction is formed, or a Schottky diode is formed. So Schottky diode means one compulsorily you will have a metallic region, one is going to be heavily doped n-type region or p-type region depending on your device for operation. And you know it is a unipolar device because I have only purely n-type or purely p-type. So either if it is n-type, I will have electrons as majority carriers on both sides. If it is P-type means I will have holes as the majority carriers on both sides. So almost you can say the depletion region is very, very minimum. So in forward bias, the depletion region is very, very minimum, and the electrons are going to take this advantage and they are going to cross the depletion region and constitute the flow of current. So it shares the advantage of point contact in which there is no significant current from the metal to semiconductor in reverse bias. So it is just like when you reverse bias a junction, there is no current at all. The current in the reverse bias is going to be exactly equal to zero. Whereas in conventional semiconductor diodes, you have the concept of breakdown, right? But since you have a metal semiconductor junction here, when you reverse bias your this Schottky diode, there is no significant current flow in the reverse direction. Okay, because the metal, the Fermi level of the metal is very much lower than the Fermi level of semiconductor. So it takes huge amount of energy for the electrons to go from the lower level to the upper level. That much amount of energy is not available in the form of the biasing. So significantly, they say that there is no significant current flow from the metal to semiconductor when you are going to reverse bias your Schottky diode. So this is the a symbol of Schottky diode. This is the Schottky diode. See, Schottky diode is different. Schottky barrier diode is different. Schottky diode is a simple metal semiconductor junction, and the difference you see, it is diode with S. A triangle with S is going to be Schottky diode. Schottky barrier diode means I'll have two contacts. One is a Schottky barrier contact, and one is going to be the ohmic contact. And see this representation, you will have a triangle followed by inverted S. So this is Schottky barrier diode. This is going to be normal Schottky diode. To understand the difference, what is similar to both means metal semiconductor junction is going to be similar to both. Okay, and how you fabricate differentiates your Schottky barrier diode and your conventional Schottky diode. So the delay present in the junction diode due to electron-hole recombination time is absent here. That's what we saw. We told that the minority carriers are absent. So the time taken for the device to switch on from on to off state and off to on state is going to be very, very minimum. And there is a larger contact area between the metal and semiconductor. So the forward resistance is less and the noise is less. They say that it is a point contact. See, the Schottky barrier diode, the metallic region is making contact with N plus only at this point, correct? It is a minimal area of contact. But in Schottky diode, you see the interface between the metal and N plus is going to be complete. You are going to have an area where the contact between metal and semiconductor is going to be formed. So because of that large area of contact between the metal and semiconductor regions, the forward resistance is going to be very, very less, and the noise is also going to be very, very less. Already this is a unipolar device, so noise is already divided by 2. It is half of the noise, because when you have a bipolar device, you will have noise due to electron plus noise due to hole. When you have a unipolar device, either you will have only noise due to electron or noise due to hole. So that 50% of noise is getting reduced. And in that 50% noise, even in the 50% noise, you have a reduction in noise because the forward resistance is lower, because you have a larger area of contact between the metal and the semiconductor junction. So when you are going to forward bias, the electron is going to flow from semiconductor to metal, and the reverse bias, the reverse direction of flowing from the metal to semiconductor. You know this one, because in the energy band diagram, we have seen the Fermi level of semiconductor will always be higher than the Fermi level of metal in forward bias. So when the electrons are going to flow from upper energy level to lower energy level, their energy is taken from the forward bias and they will constitute what is called as current. Okay, so there is no there is very little minority injection, or I can say there is no minority injection in these types of diodes. So we can say Schottky barrier diodes are going to be majority carrier devices. The minority carrier effect is going to be completely ignored here. So practically, you will have some very small effects of minority carriers, but literally, ideally, you will have some effect, but practically, you can say that ideally zero effect, and practically there will be some effect of minority carriers, but you can call Schottky diodes in general to be majority carrier devices. So you can see the PN junction diode and Schottky barrier diode characteristics. So you can see the turn on time for your Schottky barrier diode is very quick. It occurs at 0.4 volt. That's what we have seen in the properties slide. It occurs at 0.4 volt. But same thing for PN junction diode, it occurs at 0.7 volt. So you can say this diode is going to turn on faster compared to PN junction diode because of absence of minority carriers. That is the major reason why Schottky barrier diodes have a very small cut-in voltage compared to your PN junction